Hey everyone! In this last video I'm going to talk about clustering. So we're going to continue our discussion of ideological positions in US Congress, and specifically we want to explore how congressmen are clustered, to what extent they're clustered ideologically across party lines or within party, right? And so, kind of, if we kind of continue our argument related to kind of increasing polarization in the United States, the argument would be if this increasing polarization leads to legislators clustering with members of their own party rather than with other without party members, right? But while if you remember the kind of graphs that we looked at in the previous video, you'll already saw that there were clear clusters for each party, or differentiating both parties. But of course, we could also ask, what about clusters within each party, right? So even beyond kind of the broad polarization between party or cross-party lines, we could also be interested in exploring clusters within each party. All right, so how can we identify these clusters? There are a lot of different clustering algorithms that allow us to discover groups of observations that are similar to each other in a multidimensional space, right? And so this is kind of an example of descriptive or exploratory data analysis where we have some multidimensional data, or in our case, it's the two-dimensional data with a lot of observation, a lot of congressmen, and we're trying to find structure in that data set. And we're trying to kind of identify groups of observations that are similar to each other on those two dimensions, right? And so there are a lot of different applications going beyond this ideological clustering that try this kind of what we call unsupervised learning, which is discovering hidden structures in the data based on some multidimensional input. There are applications in text analysis and network analysis that kind of use these methods, right? And this is opposed to supervised learning, where we're trying to predict some outcome variable for an unlabeled portion of the data based on training a model for a labeled portion of the data, right? This is a very important distinction between supervised and unsupervised learning. We're going to come back to that throughout the semester. But for now, what is important to remember is that kind of this clustering exercise that we're going through is in this video is an example of unsupervised learning, where we're trying to discover some structure in the data that otherwise we wouldn't be able to see. Okay, and one very basic algorithm to identify these clusters is called the K-means clustering algorithm. And this K-means clustering algorithm works as follows. We ultimately start with a set of initial centroids of K clusters. So we set the number of clusters that we want to extract from our data, and then we randomly start with some initial starting points in our example two-dimensional space. And then given these centroids, given these points that we assigned, we assign each observation to a cluster whose centroids is the closest in terms of Euclidean space. So the square root of the basically summed squared distance across all dimensions to that observation, right? So in other words, we drop a couple of pins in our two-dimensional space and assign each observation that is closest to one pin to that cluster. Okay, and then in the next step, we choose a new centroid for each cluster whose coordinate equals with the within cluster mean of the corresponding variable. Right. So ultimately, that means first we put a pin somewhere into the two-dimensional space. Then we assign all the observations that are closest to that pin to belong to that cluster, right? And then we compute the mean of that cluster that we just defined, and then we set the new pin to that mean of that cluster. Okay, so now we have a new centroid. We kind of move the centroid a little bit, And then ultimately what we do is we repeat step 2 and step 3 until cluster assignments no longer change, right? So the cluster kind of centroids move a little bit through that two-dimensional space until at some point it converges and it doesn't move any further, right? Now we're going to go through an example of discovering clusters using this Congress data that I discussed previously in the previous video. And so I'm just loading the Congress data here again, but we already have it in our workspace. Ultimately, we want to create an input matrix to generate our clusters. So in our case, we create two matrices. One is based on the 80th Congress, and one is based on the 112th Congress, and it contains basically the DW nominate scores on the first and second dimension for both congresses, right? And so those are two column matrices, right? And the rows are the observations, the individual legislators, ultimately, right? Here we are using cbind to combine objects by column. We could also use rbind to combine objects to bind them together by row. Okay. There are a couple of useful operations in R that we can use for matrices. For example, if we want to compute the sum across all columns, or the row, the sums across all rows, or the average across all columns, or average across all rows. But in general, we can apply a function across all columns or all rows in a matrix using the apply command, and we'll talk more about the apply function later on. Ultimately, for now, one thing we can do is we can directly, using these two matrices that we just created, we can use the Kmeans command to compute the average position on both the first and the second dimension in the 80th Congress and in the 112th Congress, right? And so the Kmeans DW nom 80 gives us two outputs, which are the average positions on the first dimension and the second dimension in the 80th Congress across all legislators. Same for, we could do the same for the 112th Congress. The point is here that kind of the alternative, rather than using the Kmeans command, we could also use the apply function. If we use the apply function, the input is again our matrix, our input matrix. This second argument 2 means that we're applying a function by column. If this argument is 1, then we're applying a function by row. And the function that we're applying is the mean, the average, okay? So now, in order to use the Kmeans algorithm using these data, we just use the Kmeans command. And as I said first, when we kind of went through the logic of the Kmeans clustering algorithm, the first thing is that we have to specify the number of clusters. So that's something that is chosen by the researcher. In our case, we want to look at 2 clusters in the first step. And so the Kmeans argument, the Kmeans command, takes as a first argument the matrix based on which we want to find clusters, and then the centers argument specifies how many clusters we want to identify. And we're saving that output in our in 2 new objects. One is K82, so that's for 2 clusters in the 80th Congress. And 2 clusters in the 112th Congress. Okay. It is worth kind of exploring the output that we saved here in a little bit more detail. We can, in general, this output that we saved is a list containing multiple elements of different types. Right. If we look at the names, if we use the names command for this output K82.out, we see that there are 9 different elements that all contain different types of information that are part of this K-means algorithm, right? So we have cluster, centers, and a couple more elements that we can look at, right? we don't need to worry about all each individual one of these elements. For us, what is most important now is that we can extract the resulting centroids again using this dollar notation. So this is kind of similar to identifying variables in a data frame. Now we have a list, and we can extract individual elements of that list again using the dollar notation, right? So if we call k82.out dollar centers, that means we're extracting the centers element of this object, and this gives us a matrix, a 2x2 matrix of the coordinates of the two cluster centroids. Okay. So we could then use this information. So in addition to having the centers, so the centroids of each of those clusters, we can also extract information about which of these which observations are ultimately assigned to each individual cluster, right? So here what we're looking at is a frequency table where we look at the actual party of each individual congressman and the cluster that we extracted based on our unsupervised algorithm, right? So ultimately what we see here is that down here we have the different parties that we are actually of the congressman, and we have our two clusters 1 and 2, and we see that Democrats, 132 Democrats are assigned to cluster 2, 62 are assigned to cluster 1, and we have 247 Republicans assigned to cluster 1 and only 3 Republicans to cluster 2, right? So there is still a lot of overlap, right? There are still Democrats that belong to the majority Republican cluster, and there are few Republicans that belong to the Democratic cluster, right? And if we do the same, this is the 80th Congress, so 1947 to 1948. We can do the same thing for the 112th Congress, and now we see that we have much more separation, right? If we look at the cluster assignment across party, we see that all Democrats are assigned to cluster 2, and all but 1 Republicans are assigned to cluster 1. So much clearer separation due to polarization if we just look at these 2 dimensions of roll call or roll call based ideology, so to speak. We can also plot the results of this Kmeans algorithm, of this clustering exercise. In this case, we're going to look at the clustering for the 80th Congress specifically. Again, this is going to be a scatter plot where I look at just the input is basically the entire position, the positions on both dimensions for each legislator. And then importantly, we are going to set the color of each individual data point as the outcome of the clustering algorithm in order to visualize how the clustering algorithm kind of assigned each observation to one cluster based on the K-means algorithm. Okay. A little bit more information about the x-axis, y-axis, and so on, and then we're adding additional points, which are the centers. As if you remember, the dollar centers command gives you the position of the centroids of each of the clusters. So by kind of adding additional points for the centers, we kind of also identify the centroids of the K-means clustering algorithm after it converged. Okay, and so this is the result of that exercise. Again, this is based on the 80th Congress, and we see that we have mostly Democrats up here in this cluster and Republicans down here. We have the 2 cluster centroids up here and down here, and we see here those are the Democrats. If we remember this contingency table that we looked at earlier, those are the Democrats that were assigned to the first cluster together with majority Republicans, right? And those are a few Republicans that were assigned to the same cluster as the Democrats, right? So as you can see here, in this two-dimensional space, the clustering algorithm didn't perfectly separate Republican and Democratic congressmen. This looks, of course, very different if we kind of look at the same exercise for the 112th Congress. The commands here are the same. We're just looking at the positions in the 112th Congress. We're looking at the colors based on the clustering for that for those ideological positions in the same way that we did before. And again, we're adding the cluster centroids, two cluster centroids in this case again. And here we have a much more clear separation than we had before. We have Democrats here that are assigned almost exclusively to the first cluster, and we have Republicans here, and the centroids of the clusters are perfectly kind of within the cloud of Republican and Democratic congressmen. So we can see here that based on this ideological information that is based on actual roll call votes, we can perfectly recover the party setup, party affiliation of Republican and Democratic congressmen just based on their ideological positioning. Okay, and that's a product of increased ideological polarization, of course. As I mentioned earlier, we can also look at within party clusters, and that can be interesting beyond just focusing on polarization itself. And here the comparison is quite interesting because when we look at the 80th Congress, we have a clear kind of clustering of two clusters within the Republican and the Democratic Party. But if we apply the same Kmeans clustering algorithm with 4 clusters for the 112th Congress, we see that the Republican congressmen are one uniform group, and we have 3 separate clusters for Democratic congressmen that differentiates mostly on this racial conservatism, liberalism dimension. All right, so I went through this rather quickly. So if you have any questions, let me know in the Q&A session or post questions on our discussion forum. And as always, I will post the code on our Studio Cloud as well. And so I would recommend going through the slides, watch the videos, and going through the code as well and running each individual step, and kind of playing around with those plotting functions. Maybe, you know, try a clustering algorithm with, six clusters or something like that, and just see what the results look like, and kind of explore a little bit beyond what I have shown you here. All right, that's it. I'm looking forward to talking to you next week in the Q&A session, and I'll talk to you then.